welcome to lesson 1-4. In this lesson, we are going to be looking at arithmetic sequence and series. Before we leave this entire lesson, we should be answering the question, what is an arithmetic sequence and how do you represent and find its terms and their sums? In this particular video, we'll be going over the model and critique, I think that's what it's called, and the example 1 and 2. So the critique and explain is where we'll start. Model and critique, I got them a little confused. The learning target and goal is I can interpret arithmetic sequence and series. In this problem, we're going to be looking at Yumiko and Hugo, and they have two different ways of thinking about this pattern. So we've got an input-output table. At an input of 0, we're at 1, 1, 5, 2, 9, 3, 13, 4, and 17. As we go throughout, I love arrow roads. I've told my students for years that I just enjoy kind of keeping track of things through arrow roads. So I like, oh, excuse the mess on the board. Let me clear that off. I like to do a kind of just jot down the pattern off to the side. And so just thinking about this ahead of time, I'm looking at this and I'm seeing that with each value that they're giving us, we are increasing by 4. So as we go through this, you should be on page 13 of your student companion. There's Mrs. Conway. And so as you're here, you can also be working in the interactive reader, but don't type anything in right in your student companion. So describe the pattern Yumiko found for finding an output. And so I have to lose my beautiful arrow roads a little bit as I scroll down. But she found this pattern where for the first term, and so remember that this is function notation, for the first term, she took 1 plus 4 and got 5. For the second term, she took the first term plus 4 and got 5.
Plus 4.
Plus 4 again.
No, this is f of 1 is just like referring it up to there. So then, yeah, so plus 4 again and got 9. And then here you're taking that previous answer, f of 2 just gets plugged in, so 9 plugs in. That's what they showed here.
Mm-hmm.
And then plus 4 equals 13.
So really, this quantity right here is equivalent to this quantity right there.
Yes.
So this is an equivalent statement as we move. Here's one way to write it in function notation. Here's another way, and if you think back to your Math 1 class, what we think about here is, I'm going to write right over this. This is what we have now, and over here, so now plus 4 gives us our next. And so as Yumiko is looking at this pattern, that's how she's thinking about it. She's thinking about the previous term, plus 4 gives us the next term. So you could write something about that up here in A. And when we go on to part B, we're looking at the next student, who happens to be Hugo. He writes this also using function notation, but instead he writes 1 plus 4x. And so he's thinking about this in a more direct manner, not thinking about the previous term and adding 4 each time. He's considering it like, hey, here's the rate of change. Looking back up at this table, we see at 0, the output was 1.
So I think in your notebook, that in your workbook, what I would do is the words that are going to come up, we're just giving you a preview to the words. You mentioned the word recursive. This means these, when you refer, I always think recursive refer. It refers back or returns back to the previous value to get the next one. So this is called recursive. Wherever, like if you wanted the 50th one, you'd need to have the 49th before you could add 4 and get to the 50th. Hugo, this is called explicit, and this book also calls it in the general form. So maybe just make a note of that. They're going to define these a little bit later in your examples, but just to get an idea, this one is explicit because you can just go right to number 50. If you plug in 50, I'll tell you the term. Here, if I can't just plug in 50, I would need 49th plus 4.
That's great. So as we go, compare the two methods. Which method would be more useful?
Spill the beans.
Spill the beans. But that's okay, because as we go through, we're kind of thinking, okay, this is one way to do it. This is another way. One has some benefits, two has some benefits, and so we can use either. When we get to example 1, what we're really looking at is understanding what an arithmetic sequence is. And so we have another new word called the common difference. And so our first question is, oh, you're not on the pen, sorry about that. What is the next term in the sequence?
So most people love this kind of question, just what's the next one? You can figure it out, see the pattern. And if you keep pushing next, you can see your way through, and they'll show you a table of the values, and then could you figure out what the next one is? And using those arrows like she was talking about, you're thinking, okay, plus 5, plus 5, plus 5. The next one would have to be 28. So that part's easy. It's the notation is the only thing we need to keep, that we're here to kind of really teach you about. And the definition here, if you have your notes, that packet for Unit 1, it's about page 5 or 6 in there, and you'll see a blank for arithmetic sequence. And what it is a sequence with a constant difference. So what I wrote in just my own language was, it goes up or down by the same number every time. So arithmetic, I think add, as opposed to geometric, which is in chapter 6, I think.
And that's where we'd multiply in the pattern.
And that's multiplying every time. So when you multiply every time, that's more like exponential, when you did that with the now next. Adding every time is even easier. It's just linear, right? For that explicit formula, like what Hugo wrote.
Yeah. So as we continue through this example, like Mrs. Conway said, make sure to kind of keep this common difference, because that word is going to come up. They're going to use a D to represent it.
What number was added or subtracted every time?
So with our common difference here, the next term, so we have our now plus our plus 5 gives us our next. And I think I'll jot that down. So now plus the common difference gives us our next.
And then I'm going to get ahead a little bit, which you're going to see this in the homework, and the notation is what is killing kids. So just a couple things. If this was an equation, the first thing is always the first term listed. If you have a list of numbers, you have to assume the first term is term 1. So if I was going to write an equation for this, like just a good old linear equation, just think back about that. Y equals mx plus b, right? Y equals mx plus b. Well, I bet you know here, the growth is 5. That's our slope. Or if we graphed it up 5, the slope would be 5. And then we'd have our x. But b represents term 0, if you remember that. So let's go back one more step. Instead of 3 here, for our b value, it needs to be -2, because I need to go back 5 from that. So that would make this -2. So this would be like an explicit formula, but they don't ever use y's and x's talking about sequences. Instead, they'll use a. So okay, let's say this was function notation. Then this, they would use a for arithmetic and n for what number term you're on. So it might look like 5n plus -2, or -2 would be fine. But this would be what, if it says write a general formula or an explicit formula, they'd be maybe looking for something like this. The other thing that they sometimes do is a subscript. And again, it's just, these are equivalent. It's exactly the same thing. You'd say 5n minus plus -2 or whatever. I mean, just identical. But sometimes the term that you're referring to is the lower down, the subscript. Should we write this one as a recursive also?
Yes.
As long as we're on it? So this is explicit, is what I'd call that. That's like a linear, good old straight line equation like you
Well,
do.
actually, we're going to come to it in just a second, so I think we can
We'll
wait.
with that one.
I do think, though, a topic that came up and with this notation here is that we're a sub n. And so if this is the term that we are currently on, it could be the 9th term, it could be the 1st term. How would we go back one term? How would we represent going back one term? And so remember that we could do that subscript where we're taking one away. So if this was the 9th term, this would be the 9th minus 1, giving us the 8th term. Or we could go forward 1, and we have to be super careful because this is sloppy. What I need to do is make sure that my subscript looks like a subscript. So this would be going back 1 term, this would be going forward 1 term, and this would be the term we're on. So kind of some good conversation around notation. So how could we write a formula for finding the next term in the sequence? We may have gotten a little bit here, but I think that conversation, connecting it with slope and your previous work with linear equations, helps
the
it
recursive one that we said.
when we kind of think about this globally.
So here's exactly that recursive formula that we were just talking about. To get the current one, I need to go back 1. So they're using an F instead of the A that I mentioned, but F n minus 1 means previous term plus 5. Whenever you use recursive, you do need to make a point of where did you start? What's the starting number?
Identifying the starting
So you would
term.
always say F, so what you'll see is, you'll see it written as a piecewise function, like in our last section. They'll say F of 1 equals 3, and then for all the next ones, I would, F of n, I would take the previous, so n minus 1 plus 5. So I'd say, what's this? If n equals 1, it's this if n is greater than 1.
Yep.
And so it's kind of like that, I kind of wrote this wrong, but it's that idea of
No,
having
it's
two
just what it,
pieces.
so it is right over here. So we kind of have the same thing, except now we're bringing in that notation with intervals that we talked about before. The domains are different.
Oh, silly.
This is the connection that we're kind of really making that global connection between 3 different ways to write things. One with an F, one with an A, and one that explicit formula that we'd really just prefer, y equals. So,
And now here's with the n and the subscripts, same exact thing though.
if you have space, this is our general formula. So whenever
No, it only calls it recursive.
Oh, I'm sorry. So our recursive, but this is our generalization where what we're thinking about is if we had another pattern, we could slot in the D and kind of rewrite it that way.
Yeah.
That's what I mean by,
It's in this book though, they say general formula, and what they mean is explicit equation. And if they say recursive, then it's the one that returns to the previous.
So in this one, we just have to decide if this pattern is arithmetic. So as we go, we identify our starting value. We identify that the common difference, D, is 3. And so our starting value is 4. We take the previous term plus 3 to get any of the next terms. And so if I was going from this to that, I'd say, okay, well, the first term is first. It's not 0. And that's really important that this is the first term given. If we went back to the y-intercept, we'd be going back a term. Does that make sense?
And so for recursive, you don't need to go back to the 0. You can just say, here's where I start. But when we get to the explicit, you do need to go back to the 0.
I believe we'll let you try it, but make sure to check your answer. So make sure to type, Ruth is doing a fantastic job, and then check your answer, or just a space bar works, but to give yourself a star and give yourself feedback as you go. Next. So this is example 2, and we need to be able to relate between recursive and explicit.
Okay. Let us do that. So if you, whatever they give me, I would jot down a little piece of what is this even telling me? Okay, this is telling me that the first term is 3, and then every time after I'm gonna add 0.5. So 3.5, 4, 4.5, I just need to see it, and then I know what I'm working with. So an explicit definition, this is just a what can be a y equals mx plus b. They wrote it a little different because they say you can start with the first term, and then if I distribute, I'm subtracting off that difference. So this is just kind of a generic way to show that they're starting with term 0. So see. Let's just so they go ahead and they write out their pattern just like we did. And then what I would do here is just what we did on the opener. I would go back and say, okay, if this is term 1, term 0 must be 2.5. I know the term 0, I know the slope, so I could write this thing out. And I might change the format, I might change the letters that I'm using, but at least this will get me started. I know I'm going up by 0.5 every time, and I started at 2.5. And so compare that to what we see here as we push next, next, next.
I think down first.
Down. This way. Cool. Can we do it with the other pen? You're so good at it. Oh.
I can ban it, yes.
But, oh. No, it's okay.
I like to say, take a drink of your Coke. It is okay, because
Oh,
we
there.
just need to go back here and finish out this
Sorry.
problem.
Yep, next. Okay, I don't want to start over.
No, but I think this is very worthwhile talking about, because they're using this generic, like Mrs. Conway said, definition where they're taking the first term, so this is our A,
This is A sub 1 plus the,
n minus 1 times d.
so that matches up to what was going on up there.
But if we distribute this, we're gonna take 0.5, oh, you got the good pen.
So if I was distributing, I would take 0.5 times n, so okay, 3 stays, plus 0.5 n minus 0.5, right? Because this part came from distributing within the parentheses. 3 minus 0.5 is 2.5, right? That matched up with what I did too, because this is their way of going back a term from 0 and then still keeping the slope, what we know the slope is. So this, you can figure it out yourself. And on the homework, you do have to simplify. So they're gonna want this form. But if this makes more sense to you to build it, that's awesome. I've been pushing these things.
Oh, that's quicker.
Done this spray bottle.
Oh man, if you're still with us, I'm very proud of you. Given the explicit definition of 16 minus 3 times the quantity n minus 1, what is the recursive definition for the arithmetic sequence? So now we're going from the explicit to the recursive, the opposite direction we just went.
And I still find it helpful, no matter what, to write my first few terms out. Like, plug in 1. What do I get? 16.
So we can do that because we know that the structure of this equation is such that this is our first term, so here's our 16.
Yep.
And so our a sub 2, we would be taking away 3. So I'm predicting that we would have 13, and then we'd have 10 for our third term.
And if you don't recognize the pattern yet, you just want to kind of input-output, you can do that too. But I would always at least jot down the first few terms, so then you can get a good idea of what you're aiming for. So you always are going to start with your term 1. So literally just writing this into here. And then the other part is going to be dependent on the previous. So previous, take away 3, is how we're going to get our next and our next and our next.
And my first inclination was slightly different. I wanted to simplify this to get 3n, and then I have to do that minus 3 times a negative 1. So here I plus 1.
So 19 would be your term 0. Minus 3.
I like this format a little better. So I would kind of think back, there's my 19, and it was a little counterintuitive. You saw me pause, and Conway picked up because I was like, did I do it right? Did I make a sign error? But this confirms that I didn't. And that's what I love about math. Okay, all right. I think
Circle on the bottom. Do we have one more circle?
we have one more circle, but that's your try it. And so as you look at this, we can identify based on that generic structure, hey, this is our first term. This is a sub 1. Every term, we're going to take away 2, and so we can write that explicit definition. Again, I really highly recommend giving yourself star, giving yourself feedback, so if you know if you're on the right track or not. Thanks for watching.
See you next time.